So welcome all to week 3 tutorial for the course Essential Mathematics for Machine Learning. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. So the topics that I plan to cover today is eigen decomposition. We looked at some part of eigen decomposition in the last class. I'll just go over that again. I'm not going to tell you how to find eigenvalues or eigenvectors. I discussed it in the last class. We'll directly go for eigen decomposition. Then we will discuss about what are singular values and how do we find singular value decomposition. And maybe we can discuss why are they so important in area of machine learning. Why are they so useful in the area of machine learning? Okay. So last time I gave you an example. Okay. So one more thing, if you have any problem or any doubt during the session, you can unmute yourself or you can type your problem in the chat box. I'll try to solve that problem. Okay, so last time we discussed something. Let's say you have a matrix A. You found out its eigenvalues. Let's say this is lambda. This is n cross n matrix, and you found out n eigenvalues, and then you found out the corresponding eigenvectors. Okay, so then you can write A as product of three matrices. Okay, where first matrix is such that your V1 is first column of matrix A, V2 is second column of your matrix A, and so on. So this is again a n cross n matrix, right? Because each vector is of length n and you have n of them. Okay, and you will have a diagonal matrix. We call it generally P. And then we have a diagonal matrix whose diagonal entries are your eigenvalues, corresponding eigenvalues. The rest everything is 0. And then this is the last matrix is just your P inverse. Okay. So for some special class of square matrix, you can do something like this. And this factorization or writing A as a product of three matrix is known as eigen decomposition of a matrix. Okay. So there are sort of rules when you can write any matrix as a eigen decomposition of matrices. But the most simple or the most intuitive way to think about it is like what you are doing over here is you are writing eigenvectors as column for your matrix P, right? And then you also want to find the inverse of the matrix P. Okay. So if you want to find the inverse of the matrix P, one condition is that these vectors that you're writing as column, they should be linearly independent of each other. Okay. Otherwise, its determinant would be 0 and your inverse won't exist for this particular matrix P. Okay. So we want V1 to Vn to be linearly independent, right? So this is the only condition that people write in more mathematical way where they say Am is equal to Gm. But only thing that you should check is whether you have n linearly independent eigenvectors or not. Okay. So this is the thing that you should check. So if a square matrix has n linearly independent eigenvectors, then you can write it in form A is equal to PDP inverse, where P is a matrix that has eigenvectors as columns. D is the diagonal matrix containing your eigenvalues on diagonals and 0 elsewhere. And this P is just inverse of the first matrix that you wrote. Okay. One or two small rules that I'll mention over here. Okay. Okay. Let's say you have some matrix A, which is n cross n matrix. Okay. Then what you do to find the eigenvalues, you will first try to solve a determinant of A minus lambda I is equal to 0. From that, you get some characteristic polynomial, right? Okay. So let's say your characteristic polynomial is something of this form, that let's say lambda minus a1, lambda minus a2, lambda minus a3, and so on. And your all of these AIs are different. So AI is not equal to AJ if I is not equal to J. Okay, so all your AIs are different. That means all your eigenvalues that you are getting are different. Okay, so for different eigenvalues, let's say their corresponding eigenvector is v1, v2, v3, vn, then your corresponding eigenvectors are always linearly independent. So if your eigenvalues are different, so if you, let's say you get eigenvalue, let's say, let's take an example, your characteristic polynomial is, let's say, lambda minus 3, lambda minus 4. So if you have two different eigenvalues, then the eigenvectors that you will get corresponding to these two different eigenvalues will always be linearly independent to each other. Okay. So if you have a matrix for which you have n unique eigenvalues, then you will always have an eigendecomposition, because you will have n different linearly independent eigenvectors. Okay, so you need to do checking when you have some repetition in eigenvalues. Let's say A is a 3 cross 3 matrix, and you get like your characteristic polynomial something like this. Now your 2 is repeated 2 times, right? So your list of eigenvalues something like this. Then you will have to check whether corresponding to lambda is equal to 2, you have one linearly independent eigenvector or you have two linearly independent eigenvectors. So if you have two linearly independent eigenvectors, so two eigenvectors will come from here, one will come from one, and you will be able to find the eigendecomposition. For this case, you won't be able to do any eigendecomposition of your matrix. Okay. Okay. So this is the one example that we did in one application rather that we did in last class, is why are these eigendecomposition useful? One thing is that they are very useful in calculating powers of matrix. Okay. So for example, let's say you have to calculate a to the power 100, and if you are able to write A in form PDP inverse, then a to the power 100 is nothing but PDP inverse multiplied by PDP inverse 100 times, right? So if you see, this P and P inverse will lead to identity. Okay. And the whole expression will reduce to P d to the power 100 P inverse. Okay. And calculating powers of diagonal matrix is very easy. So let's say if you have a diagonal matrix lambda 1, lambda 2, if you want to raise this to the power 100, no matter what is the size of the matrix, you can just raise the diagonal entries to the power that you want to raise. Okay. So this is calculating, this is very easy. And then you can calculate high powers of the matrix pretty easily. Okay. So like, I'm not sure if you have done something like Markov decision process, continuous time, Markov chains or something like that. There you will find application of this matrix power. There you will see a lot of eigenvalue calculation and those kind of things. And also, let's say if you want to have, let's say, you know that e to the power x, you can expand it as Taylor series expansion, where you have x to the power n by n factorial, those kind of terms, right? Or you can find cos of x as Taylor series expansion. Okay. Now let's say in some application you have to find e to the power some matrix. Okay. Then how do you define, or how you go about it, is that you write it as Taylor series expansion. Let's say something like this. I'm not sure if this is the correct Taylor series expansion, but it would involve some power of n, some power of a, right? Then you can use this kind of thing to generalize a to the power n and can calculate e to the power a or cos of a or those kind of things. Okay. Okay. Any doubt till this point? Okay. So last time we also discussed what are symmetric matrices. So just to reiterate, symmetric matrices are, so A is symmetric if A transpose is nothing but A, right? And what is transpose? So for example, if this is a matrix, so if you take transpose of this matrix, then your first row becomes first column. So you will convert this row to column over here, right? And your second row hence would become the second column. This is how you find transpose of a matrix, right? Okay. So if your A and A transpose are same, then that kind of matrix is called symmetric matrix. Okay. So we sort of gave a hint last time, but right now we can say more formally that if A is a symmetric matrix, then for that particular matrix, your eigen decomposition always exists. Okay. And there are few more points that we mentioned. So eigenvalues are always real, right? And again, next thing is that then its eigen decomposition will also always exist. Okay. So this is one thing that you can remember. Okay. Let's try solving some question on finding the eigen decomposition. Okay, eigen decomposition is also known as spectral decomposition of a matrix. So it is just same name for two names for same thing. Okay. Okay. So we are given a matrix. We want to find the eigen decomposition of this particular matrix. So eigen decomposition was given by P dP inverse, where D has eigenvalues and P had eigenvectors, right? So to find eigen decomposition or spectral decomposition, we will have to find eigenvalues and eigenvector of this particular matrix. Okay. By now, I think you would be clear how you find eigenvalue. So we need to solve determinant of A minus lambda I is equal to 0. We need to solve this equation for lambda, right? We need to find the values of lambda that satisfies this particular equation. Okay. So this is 3 minus lambda 2, 2, 3 minus lambda is equal to 0, or this would imply, sorry, this would imply that 3 minus lambda whole square minus 4 is 0, or lambda square plus 9 minus 6 lambda minus 4 is equal to 0, lambda square minus 6 lambda plus 5 is equal to 0. This gives lambda square minus 5 lambda minus lambda plus 5 is equal to 0. For this, if you take lambda common, this is lambda minus 5 minus 1, lambda minus 5 is equal to 0. So you get lambda is equal to 5 and lambda is equal to 1, right? So the eigenvalues are lambda is equal to 1 and lambda is equal to 5, right? So now if you match the options, in all the options, you are okay, most probably we are solving it. We'll see if D is the correct answer or not. Okay, maybe you're right. I haven't solved it. Okay. Okay. So if you look at the option, in all the options, the middle matrix is same. That is 5, 0, 0, 1. So the eigenvalues that we obtained are lambda is equal to 1 and 5. So it has been written as a diagonal matrix. So lambda is equal to 5 and lambda is equal to 1. You could have written it vice versa too. So you could have had an option where you had 1, 0, 0, 5, but then you should write your eigenvectors accordingly. Okay. So the first column should correspond to the first eigenvector that you are listing over here. Okay. So let's try to find the eigenvector too. So this is the example where I'll try to find eigenvalue and eigenvector explicitly too. For other examples, I'll ask you to find. Okay. So eigenvector, let's say for lambda is equal to 5, right? Okay, so it satisfies the equation a minus 5i v is equal to 0. Okay, so my matrix A was 3 2 2 3, 3 2 2 3 minus 5 0 0 5, and v is equal to 0. So this would mean this is minus 2 2 2 minus 2, v1 v2 is equal to 0, or this would just mean that minus 2v1 plus 2v2 is equal to 0, or v1 is equal to v2. So eigenvector would contain v1 is equal to v2, right? So we can have a eigenvector as 1 comma 1. If we normalize it, we will obtain 1 by root 2, 1 by root, right? So if you look at these examples, this option has something similar, this option has something similar. We can rule out other two options. So these two options are not correct because they have eigenvector relation as v1 is equal to minus v2, which is not what we obtained. Okay, so this is not correct, this is not correct. Let's find for lambda is equal to 1. Okay, so if you carefully look at this first option, so this is the eigenvector corresponding to lambda is equal to 5. This is the eigenvector corresponding to lambda is equal to 1, and both are linearly dependent. So they are exactly the same. More than exactly the same, they are linearly dependent, right? So because they are linearly dependent, and we know that if we have different eigenvalues, so their corresponding eigenvector should be linearly independent. So this option can't exist for any matrix, not only for this matrix. This kind of P can't exist for any matrix at all. Okay, so the option left is option D, but we'll explicitly solve for lambda is equal to 1, so that for someone for whom this eigenvector calculation is not clear, we can make it clear for him. Okay, so this is 3 2 2 3 minus lambda times identity multiplied by v1 v2 is 0. So this is same as saying 2 2 2 2 v1 v2 is 0. This would imply that v1 is equal to minus of v2, and you can see that third option satisfies that particular problem. And this would be the negative of the inverse of this matrix P. So you know, for 2 cross 2 matrix, if you have A, B, C, D, its inverse is given by B, A minus B minus C, something of this sort. So you can see that this is exactly the same. So they have swapped these elements because these were same, it looks same, and they have multiplied the off diagonal element by minus 1. So this is the inverse of this matrix. So this fourth option is the correct Eigen decomposition. Okay. So whoever said the last option is correct is absolutely right. The last option is correct. Kalyan Kotu, orthogonal elements of components of what? Can you be more precise where you came across this term so that I can explain it more clearly? Okay, orthogonal projection. Okay, in week 2, 3 videos. Okay, so I'll try to explain it. Yes, somebody is trying to say something.
Yeah, with respect to this some problem, one doubt.
Okay, you can ask.
Uh, uh, 2 cross 2 matrix, if we have A, B, C, D, then what is the eigenvalue of A, B, C, D? 2 cross 2 matrix, if we have A, B, C, D, then what is the eigenvalue of A, B, C, D? 2 cross 2 matrix, if we have A, B, C, D, then what is the eigenvalue of A, B, C, D?
Okay, you can ask. I'm not sure if your voice is breaking only for me or is it for everyone, but your voice is breaking.
Hello, am I audible?
Yes, you are.
Hello,
Yes, you are audible. You can ask the question.
am I audible? No.
Yes, you are audible. You can ask the question. Hello, can you hear me?
So,
Or you can try to type
okay,
if you are not audible. You are audible, but
now it's fine. Okay.
I think it says all muted, but by whom? Priya, you are on mute, I think. Uh,
Is for eigenvalue decomposition.
Probably I'll answer Kalyan's question first because I'm not able to hear you. You can, if possible, you can please type it in the chat box. Okay. Okay. So orthogonal word, Kalyan means that two things are sort of perpendicular. Okay. So if you talk about the things that you have done in school with respect to that, orthogonal is just a more mathematical name for perpendicular. Okay. And if you have two vectors, let's say v1 and v2, we call two vectors orthogonal, right? If vi, sorry, v1 dot v2 is 0, right? So this is the basic definition for orthogonal if the dot product between them is 0. Now you asked about orthogonal projection. Okay. So let's say do something better. Yeah. Okay. So let's say you have two vectors. Okay. Okay. Let's call this vector to be vector A, and there is another vector which is a vector let's call this vector to be vector B. Okay. Now what projection means is that you want to see its image, right, on this vector A. So this is B. You want to see the image of B on A. Okay. So if you, how can you see the image? Let's say you light up a torch and you sort of see how much sort of image is formed on this. Let's say if you light up a torch from this angle, then probably this would be the size of projection that you will see. Okay, if you light and torch from this particular angle, this is the size of the projection that you're going to see. Okay, if you let's say reduce the angle, let's say you light up a torch from this direction, okay, then probably the projection that you're going to see, oh my god, I'll just open that. Okay, I think my screen should be visible now. But this is okay. Now what I was saying is, let's say if you sort of try to project it from this direction, then you will see some projection something like this. Okay. So you can have infinite many projections onto of a vector onto some other vector if you keep choosing different directions. But what we are interested in is, let's say you are interested in how far is this vector b from a, like what is the shortest distance by which you can reach from b to a. Okay. So that you can do if you draw a line perpendicular to this vector a. Okay. Or rather than perpendicular, you draw a vector which has dot product 0, right? So if you take the projection of this vector b from an angle, so if you light a torch which is at an angle of 90 degree from a, you get something that is known as orthogonal projection. Okay. And it has some beautiful properties, that this vector that you obtain, let's say this you call it c, this c is the shortest line that you can draw to join this b and a, right? This vector b and a. So this is the, so if you want to reach from let's say, so if you have something like b plus c, you want to reach to a, this is the shortest path by which you can reach. Okay. So this is something that is known as orthogonal projection. And you can extend this definition to higher dimensions. Okay. So let's say if you have a subspace and you want to project okay. So how did you project this thing? So if you recall, how is this projection given? Do you remember this? So if this angle is theta, what is cos of theta? Do you recall what is cos of theta? So this is base, that is the
Dot
length of
product
the
we
projection.
want into okay.
So this is based upon this b, right? So this is 90 degree. So that has, some people have curly base upon hypotenuse upon the length of b, right? This is cos theta, and also you have cos theta given by a dot b, right? Divided by mod of a mod of b, right? So from here you can find the length of the projection. Okay, you can cancel out these, and the length of the projection can be given in terms of dot product. So projection of b onto a is given by b dot product with the direction in which you want to project divided by length of that particular thing. Okay. Now, if you let's say you have a subspace S which is spanned by two vectors W1 and W2, and you want to project some, let's say, vector V onto space spanned by W1 and W2. So you do something similar over here. So what you do is similar to this. You take V dot W1 divided by mod of W1 plus V dot W2 divided by mod of W2. So this is the orthogonal projection of your vector V onto subspace spanned by these two vectors. Okay. I hope the idea of orthogonal projection and what orthogonal means is clear. Okay. Okay. So, Priya, you asked whether we need to normalize these things or not. One thing is that I normalized because in options all the vectors are normalized. That's why I normalized, so that I can get the exact answer. Other thing is that if you don't normalize, then you will have, like when you calculate the inverse, you will have 1 upon determinant, right? 1 divided by determinant. This is 1 by determinant. So that term will be like managed. You need not divide by the norm. but then you will have this P inverse adjusted accordingly because of the determinant. If you normalize, then your determinant would be 1, right? So it's like up to you whether you want to normalize here, then calculate the inverse. Even if you don't normalize, when you are calculating the inverse, the things would be taken care of. You just need, you can have any random eigenvectors there.
Okay. Thank you.
Yeah, these sessions are recorded, whoever asks. And you will see this on the course web page. Towards the last, there is an option called a problem solving session. There you will have access to all these sessions that are recorded. Okay. Okay. So here is a question I want you guys to solve. So you are given a matrix A whose eigenvectors are given and their corresponding eigenvalues are also given. Okay, then it is then they have asked you to find the matrix A that is given to you. Okay, so you have so you can use the eigen decomposition. You have P given to you, D given to you, and P inverse also you can calculate, and accordingly you can find A for me. So I'll give you, let's say, 3-4 minutes. Can you please tell me what is the answer? You can try solving it. So because you are given with eigenvectors, you can find the P. You can just write eigenvectors as columns. So this is 1, 2. This is 2 minus 1. And then you can write your diagonal matrix. So this is the corresponding eigenvalue is 4. So 4 here, 9 here, 0 here, 0 here. Then you can find the inverse of this matrix and write it over here. And that would be your A. Right? So you can do the calculations. Somebody says option B. We'll wait for others to verify. Let's use a tally mark to say that somebody has said this is the correct answer. Let's see what others say. So as I said, you can find its inverse. You can just swap these places. So this is minus 1, 1, and you can multiply the off diagonal by a negative sign and divide it. So 1 by determinant. So this is minus 1, minus 4 is minus 5. So its inverse would look something like 1 by 5, 1, 2, 2, minus 1. So this matrix, you can take the 1 by 5 outside. 1, 2, 2, minus 1, something like this. Somebody says option C. So we have two different opinions. Somebody else also says option B. We'll see. Probably it's just the division by 5 or minus 1 by 5 in the determinant that somebody might have missed. From here to here, I only see that it is division by minus 1 by 5. Okay. So let's do the multiplication. So this is 1 by 5. Let's multiply these first two matrices first. So this would be 4, 8. Am I doing it correctly? This is 4. This is 8, right? And then this is 18, right? And this is minus 9. I hope I have done the calculations correctly. Yeah. And then we have 1, 2, 2 minus 1. So this is 1 by 5. 4 plus 36 is 40. 8 minus 18. Right, so it is minus 10. So this is 8 again minus 18, again this is minus 10. 10 plus, sorry, 16 plus 9 is 25. So if you divide it by 5, this is nothing but 8 minus 2 minus 2. 5. So this is the matrix for which we had this kind of Eigen decomposition, and option C is correct. Whoever answered as B, I think you just missed minus 1 by 5 multiplication by minus 1 by 5 when you did inverse calculation. Okay. Okay. So initially we talked when we can find Eigen decomposition. I said if you have n linearly independent eigenvectors, then you can find, right? So let's look at an example, because all the examples that we have looked at, they always have n linearly independent eigenvectors. So let's look at an example where you actually don't have n linearly independent eigenvectors. Okay. So this is an example. So one small thing that you can use as a trick is, if you have a lower or an upper diagonal matrix, then the diagonal entries are always your eigenvalues. Okay. So because you see that the lower triangle entries are 0, so the diagonal entries will be your eigenvalues. Okay. So I know that eigenvalues will be 0, 0, 0, but I'll still solve because I just want to give you more and more examples of how to find eigenvalues. Okay. So we have to do something like t determinant of t minus lambda I is equal to 0, right? So this is minus lambda 1, 0, 0 minus lambda 2, 0, 0 minus lambda is equal to 0. So I have to find the determinant of this particular matrix that I have written, right? So this would imply, so if you evaluate along this particular column, so this is minus lambda times determinant of this small matrix, right? So again, this is lambda square, right, is equal to 0. This means lambda cube is 0, or lambda is equal to 0, 0, 0, right? Okay. So we have eigenvalues which is repeated 3 times. Okay. So if we had unique eigenvalues, then we were sure that we will get linearly independent eigenvectors, and hence it would Eigen decomposition would exist. But now, because we have different eigenvalues, let's see what we can do. Okay. So let's try to find eigenvectors corresponding to lambda is equal to 0. It would be given by a minus 0 times I, b is equal to 0. Or this is simply a, b is equal to 0. Okay. So matrix A, or this matrix A is nothing but T over here, right? So this is 0, 1, 0, 0, 0, 2, 0, 0, 0, and V1, V2, V3 is 0. Okay. So last row, if you see, don't give you any information. Even if you multiply, this is V1 plus V2. So 0 is equal to 0. So you get no new information. From second row, you get that your V3 is 0. Okay. From the first row, you get that your V2 is 0. Okay. So I said, like, if you are looking for a solution space, right, if you look at the solution space, rank of the solution space is the number of independent choices that you have. Okay. So now your V2 and V3 are fixed. You can only vary your V1. Okay. So the number of independent choices is 1. So you will have only one vector in this. So one linearly independent vector in this eigenspace. Okay. So you can choose V1 freely. So let's say 1, 0, 0. This is an eigenvector. So any other eigenvector will again be of this form only. It can be 2, 0, 0, or it will be some alpha times 0, 0, because the V2 and V3 are fixed. Okay. So we will have only one linearly independent eigenvector. Okay. So for lambda is equal to 0, we have only one Li eigenvector. But we wanted three linearly independent eigenvector, right? Because this lambda is equal to 0 was repeated 3 times. Okay. So that's why this matrix T do not have an eigendecomposition. Eigendecomposition. Okay. Okay. One very small comment. So if you have a symmetric matrix, its inverse is given by its transpose. Okay, you can check this thing. Its inverse is always given by its transpose. Okay. So yeah.
That's symmetric or orthogonal?
Okay, for symmetric matrices, okay, this, yeah, you are correct. You will have to adjust this determinant, right? But it is some scaling. So if you have, we call it orthogonal matrix. Okay. So there you have P transpose P is equal to identity. But if you have symmetric matrix, then also this is just some scaling by determinant. You will most of the time this will be true. Okay. So symmetric matrix has property that P transpose is this. Then again you will have this thing. Okay. Okay. So this is 6:47. We have some new topic to start after this, that is our singular values. So we'll take a break of 5 minutes. After that, we'll come back and start singular values. If you, in the meanwhile, if you have any doubt related to whatever we have covered till now, you can ask. Or otherwise, we can have a break of 5 minutes. Okay, somebody is asking difference between subspace of a vector space and subset of a vector. No, they do not carry the same meaning. I'll try to quickly explain. Okay, first of all, the thing that you have written, subset of a vector, it's not a subset of a vector, it is subset of vector space. Okay, because vector is just a single vector. Okay, vector space is a is a collection of all vectors, and you can talk about subset of subspace of complete vector space, not just a vector. Okay, so if you have a subset of a vector space, so let's say your vector space is V. So V contains all your vectors that you want to talk about. For example, let's say R2. Okay, so you can pick any arbitrary set out of this V. So you can pick, let's say, 10 elements out of it, and that will be a subset of your vector space, right? That is fine. Now for subspace, you know that the vector space follows some 7-8 properties with respect to the two operations that you define, that is your addition and multiplication. Okay. Now the subspace is also a subset. So W is a subset of V, and W also satisfies all properties of vector space. Okay. So this 8 or 10 properties that you have listed, W also must satisfy those properties with respect to the same operation that you have defined. Okay. So this is the difference between a subset and a subspace. Okay. So they are two different things. So subspace is a complete structure in some sense, and subset is just some random subset. Okay. So it is necessary for an orthogonal matrix to be symmetric. Let me just think about it. So the way you define orthogonal matrix is that A transpose should be identity, right? So if you take transpose of this thing, it is again A transpose transpose and A transpose, right? So this is again A transpose. Now you want no. I mean, it's not. Uh, can I think of an example? Yeah. So one thing is that for a symmetric matrix, you should consider the matrix to be a square matrix first, right? But this property may also be true for non-square matrix. Okay. So if in definition of orthogonal matrix, if you include that it is a square matrix too, then probably you can say that it should be a symmetric matrix. That also I'm thinking. Otherwise, let's say if you have a one-dimensional vector, you use it as an A, and its norm is it's normalized, then you can have this property being satisfied, right? But other way wise, if it is square root,
Yes, sir. We can think of it for symmetric matrix. Like I am trying to figure it out that P transpose equal to P inverse for that relation of
yeah,
you
I
mentioned
think
earlier.
I'm not sure why I wrote that, but I think you are correct that it is true for orthogonal matrix. That's how we define. For symmetric matrix, it shouldn't be always true. But I think this relation that you're saying, whatever you said that, where did that message go? That orthogonal matrix, I think it should be symmetric. Okay, but I'm not very confident about it. Let me just okay. So if we just look at this example, I don't think so. See, this example we have over here, okay, I'm slightly cheating over here, but yeah, this example that we have, if you look at this matrix, you can take this as an A. This is not a symmetric matrix, and this is your A transpose, and this is an orthogonal matrix, right? Because yeah, you can clearly say that this is an orthogonal matrix. You have A transpose to be identity, because this is the inverse of that matrix, and A transpose A also to be identity. So it is not necessary that it is a symmetric matrix. Okay, so we have counterexamples. Sir, I can't understand.
Thank you, sir.
Okay, so somebody says that okay, Kalyan, I think you missed the last class. I request you to please have a look at. We have completely defined inner product space in the last class. If I have some time left towards the end, I'll explain what is inner product space. Otherwise, we'll have to push it for the next class because I already did it in last class. If I have time, I've started the recording. Okay. So this is the multiplication that you want to do. So this is 16, right, plus 1. Then this is 28 plus 4. Well, this is 28 plus 4. Right. This is 49 plus 60. 17, 32, 32. I think I have made the correct calculation. If it is not correct, you can let me know. And we have to find the eigenvalues for this particular matrix. I'll just cross check my calculations with some software so that you know that I'm doing the correct calculation. You can use Python or anything. I find MATLAB to be the most quickest in terms of typing, so I'll use that. Okay, can you please tell me eigenvalue of this matrix that we have obtained, A transpose? Sorry, A transpose A. Somebody says 1 comma 81, probably that is correct, but we'll wait for others to solve. So somebody says option 2. So remember that right now the eigenvalues that you will get would be lambda 1, lambda 2. So singular values, sigmas that you call, are square root of lambda 1 and lambda 2. So if you are getting eigenvalues as, let's say, 81 comma 1, then the singular values will be square root of those values. I haven't solved, but I'm just informing this thing. Yeah, probably, if this is correct. Okay. So, okay. So I think 1 comma 81 is correct. I have verified, but let's try to solve 2. Okay. So let's T for the time being. So determinant of T minus lambda A would be something like 17 minus lambda. Now I'm skipping some steps because I think you are now familiar how do you calculate eigenvalues. I want this to be 0, right? So this is, sorry, this would mean that 17 minus lambda into 65 minus lambda minus 32 square is 0. This implies lambda square, and minus this is 65, this is 17. So 82 lambda, and this is 17 into 65, which is equal to 1105 minus 32 square, which is 1024, is equal to 0. Now, this implies lambda square minus 82 lambda. This thing is 81 is equal to 0. This implies lambda square minus 81 lambda minus lambda plus 81 is 0. This would give you lambda is equal to 1 and lambda is equal to 81. Okay, you can just solve this and you will get this answer, that I'm sure. Okay, so you have now got the lambda. So singular values will be square root of 1 and square root of 81. So this is 1 and 9. So singular values for this matrix is first option, that is 9 and 1. Okay. Okay. So now we have something called as singular value decomposition. Right. First, if you have symmetric matrix, then you won't get negative singular values. Sorry, eigenvalues. Then that's why you won't have that negative under root problem. Okay. Okay. So now, if you have a matrix A, you want to decompose it into 3 special matrices. Okay. So you want to decompose it into U, sigma, V transpose. Okay. Where you want your U matrix. Okay. So you want something similar decomposition as of eigendecomposition. There you had PDP inverse, right? But that was not possible for you. Okay, now I think why I wrote that thing. Okay, so I'm sorry about this comment that I made. I think I meant something else and I wrote something else. I'll just go back where I made that comment. Just above the singular values. Yeah, okay. So this comment that I made was not for symmetric matrix that P is equal to P inverse. So it was, yeah, it is P is equal to P inverse, but I'll just, okay. So if you have a symmetric matrix, right, and you find its eigen decomposition, so let's say S is your matrix and you have S is equal to P dP inverse, then for this particular P matrix, this matrix that you obtain are orthogonal, or in other words, P transpose is equal to P inverse. This is what I meant, but I think I missed it there. Yeah. So if you have a symmetric matrix, then the matrix that you form out of eigenvectors of that matrix, that is an orthogonal matrix, or in other words, that satisfies this property. So this decomposition can be reduced as PD P transpose. Okay. This is what I meant there. Okay. Now back to where we are. So for symmetric matrix, we have a decomposition like S is equal to P dP transpose. Okay. For any arbitrary matrix, we want something similar. Okay. So this U and V are also orthogonal matrix. So orthogonal matrix means A is orthogonal if A transpose is equal to A transpose A is identity. Or even size need not match if your A transpose. Let's stick to this definition only for the time being. Okay, this is equal to identity. Okay, your matrices U and V are orthogonal. Okay, and your matrix sigma is sort of it is not actually diagonal, but yeah, it is diagonal. So we'll see what they are. Okay. So your U, so let's say this is M cross N. Okay. Then your U matrix is a M cross M. V matrix is N cross M, and sigma matrix is again an M cross N for your multiplication to hold. Okay. And this sigma matrix will have entries on the diagonal, right? It will have entries on the diagonal, but this can be a rectangular matrix. So it can be a matrix something of form 1, 2, 0, 0, 0, 0, 0. Actually, diagonal is not very cleanly defined, but yeah, this is these positions. Okay. You will have entries on this position and rest everything will be 0. Okay. So this is the way we want to decompose any arbitrary matrix. Okay. Now, let's say you don't know how to find this U, sigma, and V transpose, or like, for example, let's say you studied today and you forgot it later on. So how do you find, let's go step by step. So let's say you want to just find U, sigma, V transpose. You just know this much. Okay. Okay. Let's see what U and V can be. Okay. Let's calculate A transpose A from this expression. Okay. So A transpose A is equal to U sigma V transpose U sigma V transpose, right? This is equal to U. Okay, so if you have, I think you might know this property that if you have AB transpose, this is equal to V transpose A transpose. Okay, so we are going to use the same property. So this is V transpose sigma transpose U transpose U sigma V transpose. Okay, so this implies that this V transpose becomes V. This U transpose U is identity because U is orthogonal matrix. This is sigma transpose sigma, right? Now, because your sigma was M cross N, then this would be an N cross N matrix, right? And this would be a diagonal matrix now. Okay, and this is V transpose. Okay, now compare it to Eigen decomposition of a symmetric matrix. This was PDP transpose, and your A transpose a symmetric matrix, you have obtained this to be equal to this matrix. So that means your V and P are equal. Okay, and the diagonal matrix is equivalent to sigma transpose of sigma. Okay, so if you have, let's say, this matrix of this form, sigma 1, sigma 2, sorry, sigma 2, and rest of the place you have zeros, right? And you multiply it with its transpose, 0 sigma 2, you can see the answer that you're going to get is going to be a diagonal matrix of form sigma 1 square 0 0 sigma 2 square. This would be this 2 plus 2 in that case, right? Yeah. So this sigma transpose sigma will have square of the eigenvalues because D had eigenvalues. So the sigma cross sigma will be of this form, right? So we have compared this thing. From here, what we can say is that we can say columns of V are eigenvectors of A transpose A, comparing these two, because P contained eigenvectors of S. So if we obtain a V such that it contains eigenvectors of A transpose A, we are done. Second thing is sigma contains square root of eigenvalues at diagonal positions, right? Okay, this is done. Now the only thing that we have to find is u. Okay, so there are two approaches. If you have obtained v and sigma, there are two approaches that you can take to find u. Approach one would involve, so if you, rather than doing A transpose A, if you do A transpose, this is u sigma v transpose, then it comes out to be v sigma transpose u transpose, and this is equivalent to u sigma sigma transpose u transpose. So you can see that u now is I, so columns of u are eigenvector of A transpose. One way is this, that you first calculate A transpose A, then you find out its eigenvalues and eigenvectors, and then you go for A transpose and find its eigenvalue and eigenvector, right? And you can obtain the complete set. Another thing is, you had this expression. This is the second approach. Okay, this was u sigma v transpose. If you multiply both sides with v, okay, so this is AB is equal to u sigma, right? And this is v transpose v. This would mean that AB is nothing but your u sigma. Okay. So let's try to write it out. Okay. So this is A, and this is V1, let's say, V2, V3, and so on, right? And this is some U1, U2, UN. This can be N or M. Just let me look at it. What was the size of this thing that I had done? This is M. So U is M, right? And then you have some sigma 1, sigma 2, and zeros elsewhere, right? Okay. So if you remember the matrix multiplication that we discussed last time, how we multiply a matrix with another matrix, or how we multiply a matrix with a row. So the first column that you would obtain out of this multiplication is nothing but AV1. This would be the first column of your matrix multiplication AV. Okay. It would be A times V1. And what would be the first column of this thing? This would be sigma 1 times U1. Right? Because other entries are 0. This is just a scalar. Okay. So from here you can obtain that your U1 is AV1 divided by sigma 1. Or similarly, UI is nothing but AVI divided by sigma I. Right? You can obtain this thing. Okay. So, sorry. So once you have obtained Vi and sigma I, rather than calculating eigenvalue for an eigenvector for your A transpose, you can straight away plug it in this formula and obtain the U matrix. Okay. Before I move ahead, like this SVD is an important concept in machine learning. So it is used at many places. I can assure you this thing. So I have tried to give you a flavor, but one resource that I think is very beautifully made. So there is a lecture on linear algebra on YouTube. It is freely available by Professor Gilbert Strang. Okay. He is a legend in teaching linear algebra, right? So in that course you have a video specifically on singular value decomposition, And I think the way he has explained is very difficult to replicate. And like if you want a very like clear understanding, I would definitely recommend you can take out some half hour or an hour to just look at this video. So this is a course taught at MIT by Professor Gilbert Stein, and there is a lecture on SVD in that list of lectures on linear algebra. You should definitely go through that lecture. Okay, it is very beautifully and explained in easy words. Okay, this is one recommendation that I have. You can try this. Okay. Okay. Uh, okay. So we had an example where we already found out the singular values, right? Why not completely find its decomposition? Or maybe we can just try at least finding out V, right? So we had lambda 1 is equal to 81, lambda 2 is equal to 1. Okay. So we have to find eigenvector for lambda is equal to 81. This is the matrix that we are interested in now, A transpose A, not the matrix A, right? This is the matrix that we are interested in, right? So T, this is called T minus 81I times V is equal to 0. This gives 17 minus 81, 32, 32, 65 minus 81, right? V1, V2 is equal to 0, right? So this is given by, this is minus, so this is 4 and minus 64, right? This is, yeah, and this is 32, this is 32. Why are we getting two different values? This would be minus 16, I guess, right? This is fine. So V1, V2 is equal to 0, or what we have obtained is that minus 2 times V1 plus V2 is equal to 0, or V2 is equal to 2 times V1, right? So as I said, U and V are orthogonal matrix. Now you need to normalize the eigenvectors that you get. Okay, so eigenvector that you can obtain from here is something like 1, 2, and then you need to normalize it to obtain, let's say, what is this, 1 by root 5 and 2 by root 5, right? So your V matrix would look something like 1 by root 5 and 2 by root 5. And similarly, you can find for lambda 2 is equal to 1, that would be given by 16, 32, 32 and 64. V1, V2 is equal to 0, or this would mean that V1 plus 2 V2 is 0, or V1 is equal to minus 2 V2. Okay, so using this, you can define this to be minus 2 by root 5 and 1 by root 5, right? So this is a matrix V for you, and similarly you can define sigma. Sigma is so this first one is corresponding to 81, so it should be 9, then 0, 0, and then you will have 1, and you can define or find out matrix U accordingly. Okay, this is how you can do singular value decomposition. Okay, Now let's talk about why is this singular value decomposition this important. Okay. So any doubt in this calculating singular value decomposition before I talk about why are these singular value decomposition important? You can either speak or you can just type or whatever is possible.
So in the case of SVD, even though the matrix is a square matrix, do we need to compute A transpose A? Directly from A, if we can compute, if it is a normal symmetric matrix, then also you have to go for A transpose A.
See, if you want to find eigen decomposition, you can straight away go. But if you want to find singular value decomposition, you will have to go A transpose A and find singular values and then find the corresponding eigenvector. Okay.
Okay.
Okay, so this question, this is some properties of SVD. I'll come to it after I do why are these SVDs important. Okay, because this I sort of okay, so this I sort of used in my research when I was solving my first problem in my PhD. So that's why I wanted to talk about this first. Okay. Okay. So there is something that is called as K-rank approximation. Okay. So what is meant by K-rank approximation? First, I'll tell you that. Okay. Let's say you have a matrix that is of a rank n. Okay. A rank n matrix. Okay. So let's say you have a n cross n matrix, which is full rank, right? Okay, I will just take some space from here. Okay. Okay. So what is the number of element? Let's say you want to store this matrix. This is one motivation that I'm giving. I'll motivate it from machine learning perspective too. So what is the size or the number of elements that you need to store this particular matrix? If it is an n cross n matrix, then you will have to store all the elements because this is a full rank matrix. You can't ignore any row or column. So you will have to store all the matrices, all the elements. So n square is the number of element that is required. For example, if it is 100 cross 100, so 10,000 element would be required. Okay. Now, let's say you find an approximation. Okay. I'm giving you a very layman kind of explanation over here. If you find an approximation A, which is, let's say 500 rank. Okay, 50 rank because that was 100 rank. This is 50 rank approximation. So this A is close to A tilde and A tilde is just 50 rank. Okay, that means only 50 of your rows are sort of linearly independent. The rest of the rows are dependent on these kind of rows. Okay, so if you have only 50 independent row, right? So what you can do is you can note down those 50 independent rows that would be of, let's say, length 50 cross 100 because 100 is the length of the row, right? And you can write down the corresponding coefficient. So what I mean is, let's say first 50 rows are independent. Okay, then rest of the 50 rows can be written as a linear combination of these first rows. Okay, so how they can be written, that you can write in very cheaply in number of elements that you want to store it in. Okay, so one application of this low rank approximation is that you can reduce substantially the number of element required to store your matrix. Okay, this can be also done. One more thing I want to mention. Let's say if this is a matrix A, and you can write it as product of two matrices such that, let's say this is n cross n, and this is some n cross r. and this is some R cross N. Okay. So if you can write it in this form where R is very small, then again you can reduce from N cross N to N cross R plus R cross N size. Okay. Even if this equality is not exactly equal, but some approximation, then also you can sort of use these kind of things. This is one motivation, right? Okay. This is one motivation. Okay. Now I'll give you something else. Okay. If you have a singular value decomposition where your A is equal to U sigma V transpose, I think confused a bit, but I'll just tell you where I'm confused so that you can confirm. Okay. Then you can write your A as summation of I is equal to 1 to N. This is Ui sigma I Vi transpose. Okay. Either it is this or it is Ui transpose sigma I V transpose. Okay. So this is just the difference. Okay, that you can check, or I'll probably cross check. Just give me a second, I'll cross check. I should have written that, but I'll just cross check which one is which one among the two is true. Just give me a second. Yeah, I think the first one that I had written is correct. Okay. So yes. Okay, the first one that I wrote is correct. So you can write your matrix in this form. So where Ui is your column of U and Vi is your column of your matrix V. Okay. And sigma I are your diagonal entries of sigma. Okay. Yeah, the first one looks correct. That is fine. So now this is the summation of n terms. Okay. So you will have U1 sigma 1 V1 transpose plus U2 sigma 2 V2 transpose. So all these matrix that you will obtain, so this is a column matrix, right? This is a row matrix. So column times row would be a full matrix, right? So this multiplied by this is something of this sort, right? So this would be a complete matrix of size m cross n if your A is m cross n, but the rank would be only 1. Rank of this matrix is 1. Okay, so there would be only one linearly independent row or column. Okay, similarly for this matrix, rank is 1, but size is m cross n. Okay, so you have, if your A is n rank, rank of A is n, right? Then you will have n such matrix of rank 1, which can be summed together to obtain A of rank n. Okay, this is what you can obtain via singular value decomposition. Okay. Now the problem that I want to solve is, let's say I have a matrix A which is of rank n, but I just want a matrix of rank k which is closest to A. Okay, So I want the matrix to be of rank K, and I want it to be as close as possible to A. Okay, how do I find such matrix? Okay, yeah, it is similar. It is the not similar to, yeah, it is similar to spectral decomposition. You had same terms in spectral decomposition. In singular decomposition, you have different terms here. Okay. Okay. So you want to find the matrix of rank K which is closest to A. Okay. Now what I mean by closest is that if you take sum of, let's say, A11 minus, if you just take this sum, A1, this is, let's say the matrix is A, the closest matrix is A. So square plus the difference of second term square, right? And so on. So you compare every term in the matrix, you take its difference with the corresponding term, you square it, and you sum it up. Okay. And you sort of want to minimize this sum. Okay. You can take the square root, that's fine. This norm is also called as Frobenius norm of a matrix. Okay. So what you want is that the Frobenius norm of A and A tilde is smallest. This is nothing but this is same thing. So you take the individual terms and you square it and take the square root at the end. You want this to be smallest. Okay. So what matrix is tilde you should choose of rank K so that you get closest matrix to A? Okay, this is the question. Okay. So there is a very celebrated theorem which says truncated SVD is best K rank approximation of the matrix. Okay. So what is truncated SVD? I'll tell you. Okay. So I told you that A matrix can be written as I is equal to 1 to n ui sigma I v transpose, vi transpose, right? Now, let's say you have arranged your sigma i's so that sigma 1 is greater than equal to sigma 2 is greater than equal to sigma 3 and so on. So you have arranged it in descending order and then you have written it in this form. Okay. Now, if you construct your A tilde, right, using just the first K of these matrices. Okay. So rather than using all the n sum terms in this sum, you truncate it to first K sums. Okay. Then this is called the truncated SVD. So rather than taking the complete sum, you have just truncated it at first K terms. So this A tilde would be the best K rank. Any matrix if you take of rank K, any matrix, this would be closest to your matrix A. Okay. This is at a minimum distance from your A. Okay. So this is what is called truncated SVD. And this is one application that is very much used for truncated SVD. You will do PCA in next week. There you will see how this is important. Okay. Okay. So there is one more thing. I'm not sure if this time there is a question of this or not. But let's say you truncated at m steps. So there were n singular values, or you had, let's say, what I mean is that you had n terms over here, but you truncated at m terms. Then there is a measure that you can define for quality of approximation, how well you have approximated your A. Although this is the best approximation that you can get, but still you want to know the quality. Like, let's say in some application, you don't know the value of m where you should stop, but you know that I should be at least this much good. Okay. So there you can evaluate this quality of approximation. So this is sigma 1 square and so on. Okay. Yeah.
Actually, there is a question this time.
Yeah.
The four singular values were given, and we have to go for a two rank approximation. So from the quality of approximation, we'll get the equation. And not only that, the order in which the question it is given like in the like decreasing order.
So
From
which
that
question
only,
is it?
yeah. So basically it is like some number n1, n2, n3, n4. From the
Okay.
option, basically n3 and n4 are unknown. So from the given option, since n3 is greater than n4, I
Yeah.
have chosen one option. But other than that, basically from this quality factor and from one relation between that n3 and n4, we should be able to compute it, no?
Compute. Yeah. So I can see
Yeah,
the
but that
question,
I
I
couldn't
think.
solve it. Yeah.
I think it's question 8. So you have some values. It is given 3, 2. Let's take 1 and 2. So 1 square plus 2 square plus some alpha square plus some beta square. Sorry, this is the rank 2
It was like 2
approximation.
square reverse. Yeah.
Yeah. And divided by some, right? So this is 1 square plus 2 square plus alpha square plus beta square, right? So this is given to you. Let's say this is 0.6, and then you have some alpha plus beta given. So you have two equation and two variable that you have to solve. Okay. So yeah, that's what you, so you can just sort of, let's say if this is 1, you can take alpha to be 1 minus beta and then replace it here. Then you will can transfer it here and you will get a quadratic equation, and then you can try to solve. Then it will be one variable left. So you can find the value of alpha and beta. Okay. So this is used to give quality of approximation. Now I'll try to discuss an application where this K-rank approximation is actually useful. Okay. This might be slightly superficial because it has some more theory that goes behind it. Okay. So I'm not very sure because I should have included something here if I'll be able to do justice or not. Okay. So there is a area called word embedding. Okay. I might have discussed it in initial lectures, but this is slightly a detour from what is there in class. Okay, somebody asked how to find K. So that is the main question. That is an important question that we are trying to solve in this particular example also. Okay, you will see why this K is very important. Okay. So in word embedding, so I said, like, let's say there is a word, I want to play, let's say. Okay. Now, I said if you look at some normal neural network architecture, you have some fixed input length, right? Let's say there are two such nodes and there is one node. So there is some fixed input length, and then you have some output based on it. Okay. But if you look at, let's say you want to process one word at a time and you want to sort of predict whether this word is a noun, it's a pronoun or a verb or whatever you want to do, words have varying length, right? Length is changing. Okay. So want has 4 letters in it, I has 1 letter in it. Then you can't directly pass this thing over here. Now we have much more advanced methods, transformer and everything. But let's say 4 or 5 years back, what people were doing was to convert every of these words into some embeddings. What do I mean by embedding is, you want to convert it to some vector in some RK. Okay. So you want to convert want, you want to convert I, and so on, you want to convert this to RK. Okay. So this is what we wanted to do. So that I think till now, even the transformers, like for the words, they have some pre-trained embeddings. I think this is Google or Wikipedia data that people use for word embedding. I don't work in word area, so I'm not sure which what exactly are people using these days. Okay. So, but yeah, so you have to find some embedding. Now the question over here is, how do you choose K? Okay. This was an important question. Okay, so k is the size of dimension. Okay, so let's say you want to convert every of these vector into a two-dimensional vector, or you want to convert it into a three-dimensional vector, or so on. Okay, how do you do that? Okay, so this was an important question. Okay, then some people did some research and they found out that there is some similarity matrix. Okay, there is a similarity matrix M, and when you choose k, sorry, when you do embedding, what your algorithm implicitly is doing some kind of matrix factorization. Okay, to be specific, it is doing case truncated SVD of some matrix. This matrix is not easy to approximate, but it is approximating that matrix implicitly and implicitly doing a truncated KSVD kind of a thing. Okay, so this thing is that people found out. Okay, now after this thing was found out, what is obvious to assume? So I said that if you do this kind of summation, this approximation is best k rank approximation, right? If you take sum is to up to 1 is to k, right? Now, rather than going till k, if you go till k plus 1, then by whatever we have discussed, you should get a better approximation. Okay. So, rather than finding an embedding in Rk, if you find an embedding in Rk plus 1, you should get a better approximation. Okay. I'm not sure whether I'm making all sense, but yeah, this is what should happen. So if you have a, let's say, two-dimensional embedding, and if you have a three-dimensional embedding, then three-dimensional embedding should be able to capture more information, and that's why it should be better, like if you want to look at that way. Okay, so this is what people were doing, but empirically when they saw, so let's say you have this axis as your dimension. Okay, and this dimension is your quality. I won't say quality, but it's some performance on underlying task. Let's say you are doing classification. Okay, task. Okay, so the quality is increased, and after that some point it started decreasing, and this point was much lesser than n. So we were not shooting the dimension that we were allowed to go. It was lesser than that. Okay, so yeah, this phenomena again, because of this problem, people had to do experiments on different values of k and see what value is useful and then pick that value. So theoretically, they couldn't come up with some k. Okay, so they couldn't come up with some exact k that they should choose. Okay. So this is one story. I just want to complete the story because this is one application where truncated SVD was being used and not very successful, but I'll tell you why this was not successful. Later on, what people discovered was, so I said that there was some matrix M that the algorithm was implicitly approximating, and then it was taking truncated SVD. Okay. Now the problem happened is that when algorithm was this calculating this M, it was making some error in approximating this matrix M itself. Okay, because of which we wanted to do truncated SVD of matrix M, but we were doing truncated SVD of matrix M tilde. Okay, and because of the error that we started with, so later on there were two terms. Okay, so there were term that was dependent on this k in error. There were two terms, and one term was increasing with increase in k, and another term was decreasing with the increase in k in the error. That was due to this approximation change. Okay, so yeah, this was the problem. So after some point, this increase was getting very dominant in the error, and that's why the performance was falling. Okay, so this is one phenomena where this SVD and those kind of things came into picture, which is quite relevant to machine learning. Okay. So if somebody wants to read more on this, so this all appears in a paper called On the Dimensionality of Word Embedding. So this is the name of paper. If somebody is interested, you might read. I read it 3-4 years back. I'm not very fresh on this paper, but yeah, this was the flavor of the paper. If somebody is interested, can go through it. And yeah, they then tried to formulate a optimization problem using which you can find the exact value of k. But this was very much like, this was not very exact, but it used to give a value which used to give quite good, I would say, accuracy. Okay. So this was not very exact, but this was the best that we had at that time. Then this transformer and those things came over, and the research interest sort of deviated from here. And now we are not a lot focused on this, but yeah. So finding k is not a very easy thing. It depends on your application, and you, even if you know your application, sometime you might have to run a lot of experiment. Okay. Whoever asked this question. Okay. So I'll get back to the question that I left out. Okay. So this is some properties of SVD that was there in the lecture. Okay. So it says that if A is your matrix for which you have found out your singular value decomposition, then range of A is given by first R column of your matrix U. Okay, so if you know that rank of A is R, okay, that you should know in hand. Okay, and the null space is given by the last n minus R column of V. Now there is a concept of first and last over here. So in order of understanding this first and last, you should remember that you should arrange your singular values in decreasing order. Okay. So first means the highest, the column or the row, column corresponding to the highest singular value. Okay. So if you see here, they have written 5 and 3 in that order. So you should pick accordingly. Okay. And for A transpose, your range is first R column of V, and null space is first M minus R column. Okay. So yeah. Okay. So you are given with singular value decomposition of A. This is U, this is sigma, this is V transpose. And there are 4 options. Okay. Now if you look at A, matrix A, if you look at carefully, from first row, you can't generate second row by multiplying with some factor. Okay. So these 2 rows are independent, hence rank of A is 2, right? And if you look at A, this is a map from where to where. So this takes as input, so you can multiply a 3 cross 1 matrix, right? You can multiply a 3 cross 1 matrix. So this is a map from R3, and the output that you will get is a 2-dimensional vector. So this is the R3 to R2 map. So rank is 2, and its null space hence would be of dimension 1. Okay. Now if you look at A transpose, this is a 2 cross 3 matrix. No, this is a 3 cross 2 matrix. Sorry, this is 2 cross 3, right? So it would be 2 cross 3 A transpose. So A transpose is a map from R2 to R3. Okay. And the rank is again 2. So its null space is 0-dimensional. Okay. So one thing that we know is that the null space of A transpose is 0. So we can ignore the last 2 options. Something among the first 2 is the only answer. Okay. Now, if you look at the range of A transpose, it is the first R columns of V. Okay. So this is V transpose, right? So we want to look at the first R rows of V transpose, because we want to look at the first R columns of V. First R columns of V are same as first R V's of V. Okay. So these are the 2 rows that we are interested in. We can ignore the factor, because if you generate by 1 by root 2, whatever you generate by 1 by root 2, 1 by root 2 and 0, you generate it via 1 comma 1 comma 0 2, right? Because you just multiply it by root 2. So this is same thing. So this is 1 1 0 and 1 minus 1 4. So this option is correct option. And you can, if there is a question, you can answer according to this 4 rules that you have. Okay. Okay, any doubt in today's content, whatever was discussed today?